Welcome to the GeneSys tutorial. In this section, we're going to introduce GeneSys hardware and software support for next-generation acceleration system research. We're going to showcase two examples that result in top-tier venue publications that use GeneSys framework to facilitate their development to demonstrate how you can use GeneSys in your research. My name is Hanyang Xu. I'm a third-year PhD student at UCSD Ag Lab. I'm one of the main contributors to the design, simulation, implementation, and verification of the GeneSys framework. The key takeaway from this tutorial is how we can use GeneSys framework to explore innovative research possibilities. First, we're going to look at how GeneSys hardware can be used in a system research. Then we're going to introduce GeneSys runtime system and hardware APIs that facilitate cross-domain multi-acceleration research in neuroscience. The first problem we're going to investigate is the data motion overhead in multi-accelerator system. We define data motion as the pre-processing communication overhead when data moves between the memory of two accelerators. This figure shows the data motion flow of the current multi-accelerator system, where one program leverages multiple accelerators to accelerate various parts of the program. We can see CPU are used to process the intermediate results, and CPU DRAM are used as intermediate storage. Profiling this data motion setup revealed that its significant impact on the overall runtime. This figure shows that the geo means of runtime breakdown for 5 applications, considering scenarios up to 15 applications co-running on server with data restructuring executed on the CPU. Here, data motion is defined as data restructuring and data movement. In the all-CPU configuration, domain-specific kernel execution comprises a substantial portion, accounting for up to 78.5% and an average of 49.1% of the total runtime. Transitioning to a multi-accelerator setup reduced domain-specific kernel runtime but increased the proportion of data motion in the end-to-end runtime, ranging from 71.3% to 97.1%. This highlights the critical role of data motion as performance bottleneck in a multi-acceleration environment. To address this challenge, the proposed solution, data motion acceleration, integrates data restructuring accelerators with each DSA, optimizing data flow and mitigate data motion overhead in a heterogeneous cross-domain multi-accelerator data center. In our HPCA 2024 paper, Data Motion Acceleration, Chaining Cross-Domain Multi-Accelerators, we propose data motion acceleration for reduced data movement, accelerating data restructuring, and enabling interoperability between heterogeneous accelerators from different domains through a cross-stack hardware-software solution. In this project, we developed the data restructuring accelerator using GeneSys architecture and evaluation framework. Specifically, we used the template-based GeneSys architecture to develop the implementation of DRX and use its software simulator to quickly gain insight on the potential improvement we can obtain with DRX. Then we synthesize DRX using the GeneSys synthesis flow and leverage the GeneSys built-in performance counters to obtain experimental results on a real FPGA board. In the DMX project, using GeneSys framework greatly accelerated feedback loop in early design space acceleration, reduced our hardware development time, and enabled us to obtain accurate performance number for experiments. The next project we're going to investigate is an ongoing collaboration with neuroscientists at Emory University. The main objective in this project is to develop an programmable ultra-low power brain implantable device that performs neuromodulation using various reinforcement learning algorithms. As the figure shows, the neural interface captures the brain signal of the experimental subject. Then the captured signal is processed through DSP algorithms such as FFT to obtain the brain state. The brain state is then fed to a biomarker detection algorithm using classical machine learning algorithms. Then the biomarker is fed to a control network, for example, an RL-based control network, to produce brain stimulation. Biomarker is also fed to policy networks that predict the next biomarker based on the current brain stimulus. This inference data is also stored for future model parameter updates. There are three interesting characteristics in this workflow. First, we have a multi-acceleration system. The brain implantable device operates in extreme power constrained environments, and only accelerators can meet the power and performance target. We have three kind of algorithm: the digital signal processing, reinforcement learning, and data analytics. Third, our collaborators are neuroscientists that use Python and high-level machine learning libraries to complete their task. These three characteristics poses three challenges for us. First, how to integrate the programming, compilation, and the execution of multi-acceleration system. Second, how to easily program applications for end user. Third, how to efficiently integrate hardware into the end-to-end application. The solution we propose is Hanyang runtime and programming environment, which is published in IEEE Micro 2022. Hanyang proposed a component and flow programming model where each component is a compute kernel that can be implemented with any accelerator with its own compilation flow. And the flow are the data and control flow between offloaded compute kernels that are managed by Hanyang. To provide a simple programming interface without learning curve, Hanyang primitives are lightweight Python annotations and API calls that can be easily integrated into the existing Python code that our current user already have. To efficiently integrate GeneSys as one of the accelerator, we developed the GeneSys Python API, which is an instance of the component in the Hanyang component flow programming model. The API abstracted away the underlying accelerator programming, data motion, and scheduling, which made it easy for end-to-end application that use GeneSys as one of its accelerator. Without the GeneSys hardware Python API, the underlying hardware execution stack is a complex system that only domain experts in hardware have the knowledge to operate on. With just a handful of GeneSys API, you can abstract away the complexity and seamlessly process your data using Python. These APIs handles tasks like compilation, hardware generation, execution, and verification, ensuring that your workflow is both efficient and straightforward. In a sense, they empower you to focus on your data and application, while the API takes care of the intricate aspect, making FPGA programming and data processing more accessible than ever. This is possible because we have done the heavy lifting and packed everything as an environment that just gets installed with GeneSys. In this section, we introduce GeneSys framework, hardware and software support for system research. We introduce two system research examples that benefit greatly from GeneSys framework. We hope the work we present here can facilitate your research in a meaningful way. The main contributor to this part of the work are Jung-Yoon Kim, Hanyang Xu, Rohan Mahapatra, and Lavanya Kasikadyan. Thank you for attending.